Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students, so we are now going into a phase where what we are going to be learning carries partly over to chemistry, and so I was going to try and introduce it in such a way that eventually there is some amount of overlap, etc. So this is essentially there are two ideas that we will be discussing here. One is the mechanical properties of fluids, right? And the other is the thermal properties of fluids. And finally, what is called kinetic theory of gases. Now these two things, um, they kind of overlap. So I'll do a little bit mechanical property, then I'll go to thermal properties. So mechanical properties deal with a certain aspect of things. Then thermal properties deal with another aspect of things. Then finally thermodynamics itself. All three at some level have significant relationship to to chemistry, to what you learn in chemistry. So let me get right down to it. So when we talk about mechanical properties of fluids, basically, as you know, there are three states of matter. In fact, there are four, but very often they don't mention the fourth. Okay. Now, the state everybody understands. The atoms mostly stay very rigid in a formation, in a solid formation, right? And liquids where there is some amount of movement inside the like a container, and there is the ability to flow, right? Change shape and flow and occupy a container, and but then it is also dictated by gravity. And then finally gases will just move around, even they are less affected by gravity, and they can occupy any space, and from the space they occupy you cannot tell their weight, or there are laws that deal with that. The more you apply pressure, things change a lot more in gases. Okay. Now solids typically has definite shape and size, except when it's things like putty, right? And so when we apply pressure to it, the change in the volume is negligible, and it may be so small that it cannot be recorded, right? Now with liquids, it is it is also true, but it cannot take shear stress, so its shape changes. Volume does not change, typically. That is a liquid. But then sometimes if you apply immense pressure, even solids, liquid, solids will crumble, and we already discussed that in the context of elasticity and everything, mechanical properties of solids. We dealt with all the things, Hooke's law, when it breaks and all that, right? Now or Young's modulus, not Hooke's law, Young's modulus, right? And then shear and stress, etc., right? So now in gases, the change in volume is enormous. When you compress a gas, it will really compress. That's why you have all these compressors, etc. Liquids, their their behavior in as you know, liquids are have hydraulic action, right? And so so that's why they are used in hydraulic brakes, right? So when we fill a tire with air, it does not go to the bottom, but instead fills the space uniformly. That is, it is not so sensitive to gravity. When we pour liquid in the tire, it goes to the bottom and sits there. Means it's affected by gravity. Since the liquids and gas do not have specific shape, they can flow. They're called fluids, that which flows, right? There is another state of matter which happens at very large temperature. Like let me take a brief interlude to discuss fluids. That which flows is called shara. And from shara comes, of course, the goddess uh, Saraswati, and of course the son of Lord Shiva, Sharavana. Okay, and Shara also means reeds. Anyway, I thought I'd keep some of you engaged with that slight diversion. Okay, there is another state of matter which happens at very large temperature, where the atoms are actually stripped of their electrons from their outermost shell, and that state of matter is called plasma. So that is, what happens is all the electrons are gone, and therefore everything is an ion, and then it's like kind of packed in. Now it is this state of plasma which is found in the sun, and this happens at a very large temperature. The sun has a lot of plasma. You may have all heard of this plasma TV, right? So, I'll not go into that. Some scientists consider colloids, which are suspension of particles, as another state of matter. But, that is only some scientists. Colloids can be considered as, there are cases where, you put a solid like sugar, right, into water, salt into water, and it dissolves, right? Colloids don't dissolve, they just hang around as small particles. The air we breathe is fluids, right? So there's a lot of processes that go on human bodies or in other living things, including plants, are mediated by fluids such as water. Okay? Water is so essential to life. There is no, it is such a fundamental. If you take out carbon and you take out water, really there is, and nitrogen, we are made of these things. Literally, you know, literally 90% of the body is water, and if you take out the remaining, there will be a very little phosphorus, very little other things, and if you take out nitrogen, then you're done for, so now solids have definite shape because of the intermolecular force of attraction is very large, so they keep the shape. In liquids, it is small, but it is not negligible. In gases, it is negligible, so they kind of move around freely, and that's what we are slowly heading towards to discuss this kinetic theory of gases. But of course, we first have to discuss these other two forms of matter. Which is heavier, block of wood or iron? Actually, iron is heavier, of course. Iron sinks to the bottom in water, while block of wood floats. Therefore, its density is lower than that of water. What is density? Mass per unit volume. If something's mass per unit volume is less than 1, it will float. If it's greater than 1, it will sink. It's as simple as that, because water is mass per unit volume is by definition 1. Rho. Rho equals mass by volume, right? Now, when something floats, it follows Archimedes' principle, right? So, so now, what is the unit for density? So this rho is called density. What is the unit for density? Kilograms per meter cubed, or in CGS system, grams per centimeter cube. Okay. So now you have iron, aluminium, water of course floats, and glass also sinks. Seawater has slightly higher rho than salt water, than fresh water, right? Mercury is very heavy, heaviest. It's a metal, but it's a liquid metal, right? Such a surprising thing, because ethyl alcohol is floats, right? Or you can mix it, of course, in water, right? Then you have air, which is which is very low, right? So compared to its rho is rho is dictated by the pressure it is under, right? And when we say standard temperature and pressure, we mean pressure and temperature that correspond with 27 degrees and room temperature and room pressure, right? Ground level pressure. Now, from the above table can be seen that the density of liquid is one order of magnitude less than that of solids, and gases are three orders of magnitude less than solids and liquids. What is the mass of a lead sphere of radius 0.5 rho, right? So very simple. Mass is equal to rho times volume. Okay, so that's a simple set of ideas with respect to mechanical properties of matter. I thought I'll spend a little more time, but then maybe it's not as useful. Okay, so now we'll go to what are the thermal properties of matter. Okay, so we looked at the mechanical properties of matter. Now we'll look at the thermal properties of matter. Now, normally when I discuss my classes, I do a little bit of promotion of our videos, of our apps, right? So in every one of our apps, you have IIT PAL lectures, right? They are fantastic lectures made and provided to students. The thing is, it's very difficult to find them, and most often you need them the most when you're reading an ebook or when you're reading a textbook, right? So when you're reading a textbook, you want to be able to access these videos. We make it extremely convenient for you along with the slides. Our apps are, and along with that, now we also have assessment. So students, they study the book, they learn from the slides, they listen to IIT PAL lectures, my lectures, and lectures of Professor G.K. Bhatt, etc. And then same time, they also learn by reading the textbook and looking at the formula sheet. Those are formula sheets, okay? And then they go about it, but from there to learn well. And of course, there's also what you learn in school. And then of course, we now have Jnana Test Prep app. In addition to e-Abhyas, you can go to e-Abhyas and learn from there. But also, when you're ready, you must take tests, full-fledged tests. If you're going to be preparing for NEET and JEE, you better be taking full-fledged tests. Then we have a lot of excellent materials for students to study. So Sushruta is for the NEET students, Ramanujan is for our JEE students, and we love to have students download and use our apps. So now, let's go back to the business we were in. Heat is the form of energy transfer between systems or a system and its surroundings by virtue of temperature difference. So the point here is that heat is a form of energy, or more specifically, when heat flows from one place to another, there is a transfer of energy. Okay, so that is the important thing. And what is an indication of the inherent or latent heat is this thing called temperature. Okay, the most common property used, right, is variation of volume of a liquid with temperature. For example, in a common, so how do you measure temperature? We have this thing called a thermometer, right? And typically it has mercury or alcohol, and these change volume linearly with temperature. Higher the temperature, bigger the volume. So you have that little thing, and then it flows as it expands, right? So its expansion is linear. And so mercury's expansion is linear, most commonly used in thermometers. So now we have three scales for temperature. One is called centigrade, right? Centigrade is the most common one used in India. Then we have Fahrenheit. Fahrenheit is a German word. It is how we in the United States measure temperature. We measure it in degrees F, but the most common one is degrees C. Then finally, there is the absolute scale called Kelvin. Okay? In Kelvin, there is this thing called absolute zero. At absolute zero, it is minus 273.5 degrees centigrade, which corresponds to 0 Kelvin. At 0 Kelvin, there is no movement. Okay, Now, normally if you had something, right, there will be some, if the liquid, there will be movement, etc. But here there is, if things go to, if there is no internal heat energy at all, latent heat energy at all at 0 Kelvin. Okay, and now at close to lower temperatures, there is also this thing called superconducting. Things become superconducting. There is free flow of an easy flow of electrons, resistances diminish, etc. Okay, so now, so how do you convert between Fahrenheit and centigrade? Remember, 9 divided by 5. Okay, so if you had the centigrade for something, you multiply it by 9, you divide by 5, and then you subtract 32 or add 32. Add 32, right? If you have the 30 degrees centigrade, multiply by 9, divide by 5, and add 32. That will give you the Fahrenheit. Okay, so normally when we say 40 degrees centigrade, people think it's very hot, right? But in the US, we normally say 100 degrees Fahrenheit is very hot. Of course, different people have different tolerances. So let's do a quick conversion. 100 degrees Fahrenheit, how do you convert it to centigrade? You first subtract 32. Okay, now once you subtract 32, you end up with 68. 68 times 5 by 9. 68 times 5 by 9 is what? So that you take your calculator, punch it up, and 68 times 5 is 5, 6, 30, 5, 8, 40, 8, 5 is 40, 340 divided by 9 is almost 40 minus 2, right? So it is 38 degrees, somewhere there. Okay, so it is no different than when you're trying to calculate, how fast a particular bowler is bowling, right? If you know what is a good speed, if they tell it to you in miles per hour, and you need to calculate in kilometers, you have to do a multiplication. This is just like that. Okay, so now to go from centigrade to Kelvin, we just add 273.5. Just add it. Okay, centigrade to Kelvin. If you need to go from Fahrenheit to Kelvin, you do a hop and then a step. Hop and step. Hop and step. Okay, very simple. Now then, let me discuss briefly this. This thing called ideal gas. See, when we looked at this behavior of matter, right? It is at the gross level, it follows some laws, but they are not perfect laws. They are rough laws. Okay, it like in the aggregate, these laws are kind of laws dealing with aggregates are very approximate. Okay, so now then they come up with this idea. So why is it? How does it work? And then they say, if it were an ideal gas, it will exactly follow these laws. And then they calculate using ideal gas equations. But when you go in the real world and you have a boss who's trying to maximize his return, and they all are, then they want you to not think ideal but real. Money doesn't grow on trees. That's the real world. So they want you to know ideal gas equation, also the real gas. Now, what are the ideal gas equations? They are the boils law and the Charles law. Now, and then there is this, what is called the ideal gas equation itself. Boyle's law is simple. PV equals constant. Okay. Now, Charles law is what? V by T equals constant. Okay. Boyle's law, P is inversely proportional to V. Charles law, V is directly proportional to T. Finally, ideal gas equation, PV is equal to nRT. From that, you can derive Boyle's law and Charles law. If temperature is constant, PV is equal to constant. If pressure is constant, V by T equals constant. Right? So just remember PV equals nRT. What is N? N is the number of moles. What is R? R is the universal gas constant, 8.3 in 10 to the power of something. I think they missed whatever that 10 to the power of something is. Okay. So So PV equals nRT. Remember the formula. Remember what R is. Remember N is the number of moles. And remember T is the temperature in Kelvin. T is the temperature in Kelvins. All right. So that, um, you remember, the exam, you'd make the conversion. If they left it in centigrade, you remember to convert to Kelvin. That's why I say it a couple of times. Most objects expand when heated, right? But this varies from object to object. Remember what is called the anomalous expansion of water, right? All of you know that ice floats in water, right? Normally, when something becomes a solid, it will become heavier. It will shrink and become heavier. Not so in the case of ice. In the case of water, when it freezes, it expands to be as a solid. Okay, this is called the anomalous expansion of water, and it expands as a solid. Therefore, ice has a density of, I think, 0.93 or something like that. It is 7% less dense than water, and therefore ice floats in water. That's why you see all these things called icebergs floating in the Arctic Ocean, right? See that all the time these days, right? So metallic lids on glass jars can be opened by placing them in hot water. Why is that? Because the lid will expand. Certain things, there is a variation in how much things expand. Glass doesn't expand much, metal expands a lot. Okay, that is thermal expansion. Okay, balloons shrink when placed in ice water. Why is that? The gas inside shrinks. Thermal expansion is increase in size when there is increase in temperature. Length, okay, so that is the whole thing. So delta L by L equals alpha T. So alpha is called the coefficient of volume expansion. In this case, coefficient of linear expansion, alpha L, right? Coefficient of linear expansion. So now delta A by A will be 2A delta T. Delta V by V will equal 3A delta T. Now, what is this A or alpha, right? 3 alpha delta T. This is called the, alpha is called the coefficient of linear expansion. Why is this true? Okay, so why is this true? Why is delta A over A 2 times delta L over L? Right? So that is, so when something expands, right, this expands, that expands, therefore, how much does this expand? So you say A plus delta A equals, remember, A plus delta A the whole square, or L plus delta L the whole square equals L square plus 2L delta L plus delta L square, right? So that is A, right? So A plus delta A equals L square plus 2L delta L plus delta L square. Okay, therefore divide this whole thing by A, right? A equals L square. Cancel those two things out. So then the remaining parts, when you look at, you have delta A divided by A will equals 2, because it's 2L square plus 2L delta L. That 2 is what produces your this 2. Okay, so it's because you have length grows as well as the width grows. Therefore, you have the area growing by 2 alpha. Okay. The third term, delta L square, is too small, and therefore they drop the delta L square term. So they keep only the middle term. Okay. That's what leads to your 2. Now, when you have tripling, right? A plus B the whole cube is A cube plus B cube plus 3A square B plus 3AB square. In that case, they drop the last 2 terms and they keep only the 3ab square term. Okay, so that's how you end up with this 3 alpha L delta T. This is a very simple, like, when you do calculus, this is very, very simple. This is a standard incremental analysis. Okay, incremental analysis like you will learn in calculus first time, right? So that's all they are doing. That's how you end up with this 3 times the linear, right? Coefficient of volume is 3 times the linear. Okay, now anomalous, we already discussed. Water expands, right? Water goes through anomalous expansion as the temperature, there is a temperature around 4 degrees at which water is the densest, and after that, when it becomes ice, its volume starts to increase again. Of course, it keeps increasing when you heat it up, and of course, after it becomes at 100 degrees, it transforms into gas, right? So the key point here is the density is maximum at 4 degrees centigrade. And this is called the anomalous expansion of water. Okay, so now when it comes to coefficient of volume expansion of what is that? Gases, PV equals nRT, P delta V equals mu R delta T at constant pressure. Therefore, delta V by V equals delta T by T, right? So volume and temperature ratio is dictated by alpha V, which is equal to dV by dt, right? I by V star dV by I by V star dV by dt, right? All right. So not I, L by V, right? So V is equal to L cube, coefficient of volume expansion, coefficient of linear expansion, and then thermal stress. So what is thermal stress? Thermal stress is the stress that develops in a rigid truss that is held in place and expands as a result of expansion or inability to do so. So what happens is that when you hinge things together, you must correspondingly, you must be careful how you hinge them. In places where there is a lot of expansion and contraction, there is stress from the expansion which leads to pushing, right? And that pushing eventually weakens the what is called truss. Okay, the term truss is a very common term in what is called engineering mechanics when you go learn engineering mechanics. So now what they are discussing is thermal stress in a truss. So because of the expansion, they push against each other, and therefore there is thermal stress. Okay, so delta V by V equals C times delta L by L. As I explained, A square, A plus B the whole cubed, right? So delta V is L plus delta L the whole cubed minus L cubed. So you actually end up with 2 terms. They drop the second term, right? And then they just keep the 1 term, and then they divide by L cubed. On one side they divide by V, the other side they divide by L cubed. So you end up with 3 star delta L by L, right? So, and therefore you end up with alpha V equals 3 times alpha L. So 3 times the linear coefficient of linear expansion is the coefficient of volume expansion. That's the point we are making here. Now, pendulum has copper rod, keeps correct time at 20 degrees. It gains 15 seconds if cooled to 0 degrees. Calculate the coefficient of linear expansion. 2 pi times square root of L by G is the period. It gains 15 seconds per day. So what is period? Okay, period is the time it takes for it to go once. Period. Right? 2 pi times square root of L by G. Right? Where does this 2 pi times square root of L by G? Where did you hear it? If you scratch your head, you will remember it didn't happen very long time ago. It happened probably in your school class in simple harmonic motion. Right? And a small pendulum forced to oscillate 2 pi times square root of L by G. Right? So now what happens to L? L is the temperature has gone up, therefore L has become bigger. From L naught it has gone to L naught times 1 plus alpha theta. Theta is the change in temperature. So it keeps correct time at 20 degrees, and what has happened? The temperature has gone to 0 degrees. Now, when it goes to 0 degrees, what happens? L declines. As L declines, T declines at the same rate as square root of L, right? Therefore, so 1 plus alpha theta to the power of half will become 1 plus a plus b to the power of n is a plus nb, approximately linear, by using a linear incremental approximation. You include only the first term, that will only have the 1 plus x to the power of n is approximated to be 1 plus nx. That's what they are doing here. T20 equals T naught times 1 plus 0.5 times alpha theta. Now, the thing is, they are saying it T20 keeps the correct time. So T0 is going to decrease the period. What does decreasing the period mean? It means it's going to go faster. Okay, it goes faster and faster, so it go more seconds in the same day. So it gains 15 seconds every day. Okay, so T20 minus T naught by T naught is what? 15 divided by, so so there, so the change divided by T naught is what? 15 divided by 24 times 3600 times 20. Forget this, 20 comes from this. Okay, difference in temperature. Delta T20 minus T naught is 20. Okay, so that's what they are telling you. Okay, so alpha ends up being 15 divided by 24 times 3600. 24 times 3600 is the number of seconds in a day. Okay, and 20 is your theta, right? Therefore, T20 minus T naught by T naught is 0.5 times alpha times theta from this formula, right? Take the T20 this side, T20 minus T naught, divide by T naught, right? Then the T naughts will cancel. So T20 minus T naught by T naught equals 0.5 alpha theta. Very simple formula, right? Therefore, from that, you calculate the coefficient of linear expansion alpha. Okay, just plugging it into this formula. T20 minus T naught is what? 20. Right? So that's the basic formula. Okay, so okay, so now we discuss this thing called specific heat capacity. Specific heat capacity is the change in temperature delta T when a given amount of heat is absorbed or given away by the body. Okay, so here's what's happening. Okay, there is heat capacity. What does that mean? You must understand that term. Very often, you must try to grasp, particularly in heat, you must try to grasp these terms. Heat capacity is the change in temperature when a given amount of heat is absorbed or given away. When you absorb heat, your temperature changes. So delta Q by delta T will give you heat capacity. Specific heat capacity per unit mass. Okay, so so molar specific heat capacity is heat capacity per mole. Okay, so this is heat capacity per unit mass. That is heat capacity per mole. Molar specific heat capacity. Okay, so now for gases, typically they speak of specific heat capacity at constant temperature and pressure. Okay, constant pressure and constant volume. Okay, so water has the highest specific heat capacity, and hence heats and cools slower than other substances. Okay, so if it has, this is very high, right? It takes a longer time. Hence heats and cools slower than other substances. What heats fastest and right? What heats the quickest is metals. That's why we use metals in cooking, right? Very quickly it will heat and very quickly it will pass the heat to whatever is being heated. Of course, it is also doesn't, it will return to its shape, much hardy materials. Now, what is a calorimeter? Calorimetry, right, is a contraption of this system to measure heat. There is a wooden jacket inside which they put some insulating material like wool, and there is a metallic container with water and a thermometer. Okay, so now the inside, the temperature is the heat is held inside. So you can do some experiment there, and all the heat will be held inside the calorimeter, right? So means by which heat content is measured. When a hot body is in contact with a cold body in an isolated container, the heat lost by the hot body is gained by the cold body. Okay, so you may have all heard of Newton's law of cooling, right? So Newton's law of cooling, what it tells you is that the rate at which something cools is proportionate to the temperature difference. Okay, when you become closer to the ambient temperature, the rate of cooling will completely slow down. Okay, so a gold sphere of 0.1, but that's not what we are discussing here. In calorimetry, the heat loss is equal to heat gained. Okay, that is the most important idea in calorimetry. Okay, so heat leaves one place, it goes to another place, doesn't go into the atmosphere. So so a gold sphere of 0.1 kg is placed for sufficient time in a vessel containing boiling water, so that it is at 100 degrees centigrade. Is then immediately transferred to a point. So now the gold sphere has been heated to exactly 100 degrees. So that's what they are saying. It is then transferred to a 0.2 kg copper calorimeter containing water at 20 degrees. The temperature of the water rises and attains a steady state at 25 degrees. Calculate the specific heat capacity of aluminium. Where's aluminium here? I think he means copper. Okay. So the change in temperature of the gold, it goes from 100 degrees down to 25. What happens to that? Right? That temperature change, right? 0.1 is the weight MST, right? Delta Q equals M times S times T, where T or M times S times delta theta. We just saw it here. There. M times S times delta theta, right? So in this case, the M is 0.1, the S is the specific heat capacity of gold times delta T, right? So 0.1 times SAU times the change in temperature is from 100 degrees comes down to 25. That is 0.1 times S times 75. That is the heat lost by the gold. It is the heat gained by both the water and the copper. The copper is 0.2 times SCU times 5 degrees. It was 20, went to 25. The water went for 0.25 kg of water times S times 5. Heat lost equals heat gained. We know the specific heats of copper and water, and therefore you can calculate the heat loss equals heat gain. Will give you the specific heat of gold. Okay, so what is the calculate the specific heat of gold? Okay, So change of state from solid to liquid is called melting. Change of state from liquid to solid is called freezing, right? Or fusion. Okay? Point at which solid liquid states are in equilibrium is called the melting point. Okay? So regelation happens when there is refreezing due to the something, you keep something in pressure, you remove it, then it freezes again. This happens in skating. You got to be very careful. Melting point at standard temperature is called the normal melting point. So today I'm going to stop here. I will be continuing with this material next class from this point on. Um, we are going to continue discussing these ideas, like most notably the phase diagram, right? And then we will move on to little bit kinetic theory of gases, and then we will go to thermodynamics. Okay. Now, all this material is very relevant to everything you will learn in chemistry. In fact, physical chemistry does a lot more justice to this material. You must learn this material very well because it's very important in chemistry, notably physical chemistry. That's why we tend to emphasize this also in physics. But it's much more important that you learn this material very well from Dr. Tiwari. Spend a lot of time learning kinetic theory of gases, etc. In the context of chemistry. They do a lot more justice there. And if you buy our either Sushruta or Ramanujan, you use the chemistry parts, you will find so many lectures, beautiful lectures. And of course, you go listen to Tiwari ji's lectures on physical chemistry. Fantastic lectures. I advise each and every one of you to spend some time visiting our YouTube channel and taking advantage of our apps. You get our apps, half your problems will go away. All right. Let's study, of course. Not in I downloaded it, doesn't get you anything. Let's get your app and keep studying, okay? And do justice. Good luck. This is early in the year. This is when you must be studying the most. People who study now never have regrets eventually. All right. So with that, I'm going to stop for today. We'll be meeting again next week for the class 11 material. And then again, this time we have changed the timings for the physics lecture. Okay. So let's plan on it, because of the change in timing. Please note the change in timing. And next week onwards, we'll come back to the standard timing. So I'll see you all then. And with that, I'm going to end today's lecture. See you. Have a great Diwali. I want you all to be very safe when you're bursting your crackers. I know all of you are very interested in chemistry, but that's not where you learn your chemistry. You learn your chemistry in the chemistry lab under the supervision of a teacher without running any risks. And you learn your chemistry from textbooks. Okay, it's not learned from crackers. So, and eat sweets in reasonable amounts and be healthy. All right, eat sweets, but of course have a very nice bath and enjoy yourself, celebrate and pray. Okay, all good things happen to students, who study hard, and I wish you all very well. Thank you.